Hello everyone, in this lecture we are going to learn about NACE MR0175 in detail. Our flagship courses are Master Static Equipment Design and PVE Light, ASME Section 8 Division 2, and Master Welded Storage Tank, as per API 650. We have curated courses to suit your learning needs, so do visit our learning platform for more details on scutoid.thinkific.com.
What is going to be learning objective? Mainly related to H2S environment, right? NACE MR0175 mainly deals with H2S containing environment, and that is also mainly wet H2S. Now, what do we mean by that? We'll come to know. Then we'll very specifically see the requirement for carbon steel plates, which we are going to use most of the time, right? Then low alloy steel plates and SS. So these are the three specific topics which will cover almost 99% of your requirement, right? These are the things which we generally use. So we'll talk about the specific requirement from NACE MR0175, which are applied to these kind of materials, okay? And very specific to NACE, okay? Whatever I'm talking about or will be talking about will be based on NACE, okay? Now you might have read lots of client specification, okay? So which kinds of add mini requirement on their own, okay? So now you'll be able to identify through this training whatever we are going to take. So you'll be able to identify what are the things which are added by client when you read the specifications, okay? So let us start. NACE MR0175. What do we mean by NACE? NACE, you can see the full form, National Association of Corrosion Engineers, okay? First, it was issued in 1975, okay? Around 50 years back. First issued in 1975. Okay? It started even 20 years back from there, okay, when first time it was used, okay? And then formally it was issued in 1975 as a group of NACE. In around 2005, it was merged with ISO, and then it was named as 15156. Okay. So what exactly 175 talks about is the material for use in H2S containing environment in oil and gas production facilities. Now, whether it is for upstream, for midstream, or for downstream, who can tell me that? When we say oil and gas production, is it meant for what? Upstream, midstream, or downstream? Upstream, okay? The production of oil and gas, okay? The equipments which are first used, when we take the crude out from well, when it is having a mixture of lots of different hydrocarbons and water and even metals, okay? H2, N2, O2, CO2, lots of mixtures is there, okay? There we use 175, okay? Now, in refineries, what we use for refineries, guys? Do we use 0175 for refineries? No, we use MR0103, okay? So that is where 103 comes into play for refineries, okay? NACE 0175 is used in upstream oil production, okay? Now, what is the need for this? Why we are learning about different metal requirement for this application? First of all, let us understand why these are different requirements. You have crude oil, which is mixed with lots of hydrocarbons. You have H2O, H2S, you have chloride, you have sulfur, you have O2, N2, you have lots of metals, okay? Now, among these impurities, okay, most of it are impurities, right? We don't intend to use them. We want to use crude oil, right? We want to extract lots of things from that. So, but these are already dissolved in that, okay? So, among this, the NACE is for what? among these impurities, metals, O2N2, sulfur, chloride, H2S, H2O, the NACE is meant for what? It becomes applicable for H2S and mainly when it is mixed with H2O. That is what we call as wet H2S. You might have heard this term, wet H2S. Wet means wet by water. Okay. So H2S mixed with water, it becomes more dangerous because that is where the ionization happens. Okay. So we'll build on that. So, you'll be having sulfuric ions in that. Okay. Now, why that NACE 0175 becomes important, or what is the reason for material consideration? Like, what is the additional things which will be required, and what is the reason for that? Okay, so what happens when you have this environment? Okay, what happens when you have partial pressure or value of partial pressure which is there of H2S? Okay, definitely when we say H2S, it is a wet H2S. Okay, now what happens when there is a partial pressure of H2S? No, it's not only H2S, but there is a temperature. There is also pH value. Okay, so lower pH value, it's more acidic. Okay, when crude oil is taken in upstream, the nature is more acidic. Once you go to refinery side, it becomes more closer to 5-6. Okay, so in this case, it is having lower pH value, which is more dangerous. Okay, so all this combination becomes critical. Chloride concentration, stress, and time. Okay, so these are the factors. If they are present, there will be cracking of material, and that is called SSC, sulfide stress cracking. Sulfide because H2S is there, stress because definitely stress is there, so stress has to be there. Without stress, that will not happen. Okay, and the cracking because the metal surface cracks because of the presence of H2S. Now, what happens? Why this crack happens? Okay, what is the effect of these parameters on the material? So let us try to understand that in the next slide. You can see here that H plus and S minus 2. Okay, these are the ions because of the wet H2S. Okay, so during presence of water, H2S gets ionized in H plus and S2 minus. The metal reacts with sulfur. Okay, in our case, it's iron which is present in the majority, so it will react with sulfide and make iron sulfide. Okay, the property of iron sulfide is that it will accumulate at the layer. Okay, it will form a layer like the layer you see on stainless steel, chromium oxide, right? So like that, it will form a layer. Now, what will be the problem of that layer? Whatever hydrogen is getting ionized, that does not escape into environment, but that is getting absorbed in the voids of metal crystal. In the structure of metal, the hydrogen gets absorbed. It dissolves in the voids which are present there. And what happens because of that? What happens because of that? It increases the toughness of material. Okay, so slowly your toughness of the material will increase, and that may lead into cracking of material in presence of stresses. Okay, so if there is a small flaw, it will start propagating. Okay, and further it will lead to sulfide stress cracking. Okay, so that is what happens in presence of sulfur. Okay, now, as we have earlier discussed, 0175 or 0103. So when you are dealing with oil and gas production, we are talking about mainly 0175. 0175 caters to that oil and gas production, the upstream business. Okay. When we talk about refineries, there the requirement governed by MR0103. Okay. So be very clear when there is oil and gas production, when you have production facilities, the plant which is involved in upstream, the code which you'll be referring is MR0175. Okay. Now the service condition, which when we say NACE, what is the service condition we are talking about? We're talking about partial pressure of H2S. We'll see the value also. What is the partial pressure of H2S, beyond which it becomes critical, and below that, it is as good as it is not there. pH value, that is also very important. Then you have dissolved chloride content, okay, in the crude. That is also very important. Temperature, stress, and last time. If all this is there, that becomes part of our NACE study. Okay, one of the other. If one is higher, the second has to be very much limited. So we'll see the requirements. That will be more clear. Okay. Now there are three parts of NACE MR0175. Okay. Part 1 talks about the general selection guidelines, which basically whatever we have covered till now. So most of it is related to that. Okay. There is no specific requirement in part 1. Our requirement starts from part 2. Part 2 talks about carbon and low alloy steel. So very specific requirement related to carbon steel and low alloy steel will be covering in part 2. So we'll see what exactly is there. Part 3 talks about, any guesses? What do you think part 3 will talk about? Part 2 talks about carbon steel and low alloy steel. So what about part 3? High alloy, corrosion resistant alloys, which mainly we are going to talk about is SS. Okay. So corrosion resistant alloys. So mainly we are going to talk about is SS. So part 2 and part 3, part 1 is nothing, very specific we can share. So whatever we have covered, like equipments and all, that is part of part 1. So we'll be starting with part 2 because it contains with specific requirements, which is going to be useful for us, or the things which we should remember. So part 2, cracking resistant carbon and low alloy steel. Now, what are the requirements? So before that, there are two options for the qualification of material. Okay. In part 2, there are two different options. Option 1, selection of materials based on Annexure 2. Annexure 2, there are detailed requirements given. So we'll see that. So you qualify all the requirements based on A.2, or the second option is basically laboratory or experimental acceptance. Okay. So selection of steel based on very specific requirements, and that has to be qualified by doing lots of testing, okay, on the actual material. So option 1 and option 2. Okay. So mainly we'll be talking about option 1 because that is where your requirement is, which you have to specify in either TDS or TDC or ARMs. So option 1 is in terms of the percentage of H2S. Okay. So you have two options, whether you will be having a partial pressure of H2S less than 0.3 kPa, or it may be more than 0.3 kPa. So if your partial pressure of H2S is less than 0.3 kPa, then there is no special requirement. Nothing special is required. You can use the material as it is, as there is no NACE requirement. So it's equivalent to NACE is not applicable. So 0.3 kPa, partial pressure of H2S. So remember, we are not talking about the design pressure. Okay. So design pressure, if you roughly code or the NACE does not talk about the design pressure requirement, but roughly to get that 0.3 kPa partial pressure of H2S, you need to have 350 kPa above atmospheric or 450 kPa absolute value. Okay. So roughly 3.5 gauge pressure. If you are having, the chances are high that this partial pressure will be achieved for H2S. Okay. Also depends upon what is the percentage of H2S. But with high pressure, the chances of partial pressure also increasing is high. Does it make sense, guys? Till this point, this is the first requirement which we have seen. If the partial pressure of H2S is more than, now how to calculate partial pressure of H2S, that is also mentioned in 175. So you can see that. Okay. Now, if partial pressure of H2S is more than 0.3 kPa, okay, then you have to follow A.2 requirement, which talks about the control of hardness value, the post-weld heat treatment requirement, PFST requirement. For stainless steel, it also talks about pH and chloride content. So we'll see that. Okay. So if partial pressure is more than 0.3 kPa, then your environment is now NACE. NACE is applicable, and the requirement of NACE 175 becomes applicable. Okay. Now, the first requirement. Okay. So A.2. So we'll talk about carbon steel and low alloy steel. Okay. So what are the additional? Both are covered together, carbon steel and low alloy steel. The first requirement. Okay. We know that because of hydrogen embrittlement or the increase in the toughness of material because of absorption of hydrogen into the molecules, okay, hardness tends to increase. So our main job is to reduction of hardness. That is the main requirement of NACE application, to control the hardness of material and also the welds which we are doing. So you have to qualify the weld procedure where that hardness is not increased. Okay. So hardness less than 22 HRC. This is for material, base metal. We'll talk about welds also. The carbon steel has to be limited to P number 1, group number 1 and 2. Okay. So it cannot be any other carbon steel. Only limited to P number 1 and group 1 and 2. It has to see the following heat treatment condition, any one of it. Okay, one of the following treatment condition. Either it should be hot rolled. That hot rolled requirement is only for carbon steel. It's not for low alloy steel. So carbon steel has to be hot rolled. Okay, so it cannot be flat rolled. That is not acceptable for a NACE requirement. It can be either annealed, can be normalized, or normalized and tempered. Now, what is the difference between annealing and normalizing? Any one of you? What is the difference in annealing or normalizing? What is the difference? So Vijay is asking what is the reason for hot rolled. So Vijay, because of the traces of H2S, okay, the flat rolled component becomes susceptible to HIC. Okay, so that is the reason we avoid flat rolled. The temperature difference, normalizing leads to fine grain, even annealing leads to fine grain. The control temperature while cooling. Okay. That is the main difference, cooling method. Okay. In annealing, it's furnace cooled, while in normalizing, it's cooled in open air. Okay. We are not talking about solution annealing. Okay. Solution annealing is different. Okay. Yeah. So both will result into fine grain. So now both will result into the reduced hardness. Okay. And that is the reason these heat treatments are asked for. Okay. So, because you want to control the hardness of material. Now, additional requirements. So, see, these are the requirements, one to one. There is nothing which we are leaving. Okay. So, please remember that. This is everything which is applicable as per NACE, we are going to cover. Okay. Second requirement is mainly related to forging. So, earlier was related to plate. Forging, there is one requirement, and that is related to 105. 105 is acceptable with hardness limit to 187 HBW, or if you convert, it's 20 HRC. Okay. So even less than plate. So it has to be lower hardness than even plate. Okay. Rod pipe fittings, which is W234 WPB. So their hardness is restricted to 21 HRC. Okay. 197 HBW, which converts to approximately 21 HRC. Okay. So that is the limitation. So see, most of the material requirement are limiting the hardness value. Okay. Most of the requirements are limiting the hardness value of the material. Bolting and fasteners, you have a different grade which is applicable, which is M grade. Okay. So in normal carbon steel, you'll be using, or normal environment, you'll be using 193 grade B7, while in this, you'll be using B7M. Okay. For 320, the grade is limited to only L7. Okay. In normal application, and for this, grade M. Okay. That becomes applicable even for nuts. 194 grade 2HM is what you have to use for bolting and fasteners. Okay. So Pratik is asking, is 266 for flange? No, for 266, there is no requirement mentioned in NACE. Okay, only for 105 that requirement is mentioned. Yeah, there are differences between B7 and B7M. Okay, I don't remember exactly what is the chemical composition and the values of yield and tensile, but both are listed separately. Even if you open the specification of 193, you will see the two different grades, B7 and B7M. Okay. M here does not mean metric. Okay. Don't think that M here means metric. Here M means a different grade, B7M, which is used for NACE. Okay. PFHT, fiber elongation, the percentage requirement remains same, 5%. There are exemption in section 8 division 1 for fiber elongation, but here you don't have that exemption. If your fiber elongation is more than 5%, then PFHT is required. Okay, not below that. Okay, sometimes we feel that if NACE is applicable and if we are doing cold forming, we have to go for PFHT. No, still the limitation is only with fiber elongation. 105 we spoke about, Suresh. So 105 is limited. The hardness has to be limited. Okay, the value is 20 HRC. The holding temperature for PFHT is 593 degrees Celsius, very close to what you have for division 1, right? Division 1, we have 595 degrees Celsius. Here it's 593 minimum, which should be there. The hardness after PFHT should go down to 22 HRC. Okay, so that is the requirement. And that is the intention also of doing PFHT. If you are doing welding, PWHT, what do you think? Is it always required? That is the biggest misconception we have with NACE. PWHT is required all the time for NACE or no? What do you think? Based on service condition. Okay, some of you are saying yes, PWHT is required. That is how we treat that, right? Because most of the specification, if you are getting form client, they will restrict this requirement. They'll ask for post weld heat treatment. Okay. Now let us see what code talks about. If your hardness of the welding is lesser than 23 HRC, okay, if you have qualified that PQR has to be qualified for NACE application, and after welding, you have to check whether the hardness of the material is less than 23 HRC or not. If you are able to achieve that with welding, you don't have to do PWST. Make sense? So if you're able to achieve hardness, you don't have to do. Suryapal, you can see HRC method. We during engineering also we do lots of test, to get the brittle hardness and HRC, so that you can find that on web also, how to calculate HRC and all. It's a hardness unit. Okay. So measurement. So if hardness is meeting PWST requirement or meeting the 23 HRC value, if it's lower, then PWST is not required. Okay. If hardness is not meeting, then by doing PWST, you bring down the hardness value to less than 23 HRC. Okay. So the purpose of doing post-weld heat treatment here is to reduce the hardness of the welds. Okay. Minimum PWST temperature is also mentioned. 593 we saw for carbon steel. For low alloy steel, it gives 621 degrees Celsius. Okay. That is the requirement for low alloy steels. Okay. Now, there is option 2, which we spoke about, right? Option 1. What was option 1? How many of you remember? We had 2 options for deciding or selecting the material. What was the first option? What was the first option? Give me that. Given NACE MR0175 does not talk about carbon equivalent. Okay. It does not mention. Now, by controlling carbon equivalent, it is found that you reduce the hardness because carbon content is directly linked with that. Okay. So option 1 is related to partial pressure of H2S. Partial pressure is less than 0.3 kPa. Nothing is required. Greater than 0.3 kPa, whatever we studied just now, that is the part of annexure A.2 requirement. Okay. All that becomes applicable. Okay. Now option 2, where you need detailed qualification. Okay. By doing lab test, and you also consider, apart from partial pressure, you also consider the pH value. Okay. So you can see on X curve, you have partial pressure of H2S. On Y-axis, you have pH values. Okay. So if you can see the 3 different regions, okay, even in fact 4, you have 0, which is less than 0.3 kPa. So if you are in 0 region, that means you don't have to do anything. Nothing will become applicable. If you are in 1, the requirement will be a little bit more. For 2, again more. And 3rd is the critical most. Okay, so there are 3 main reasons for source service. 0 is for no source service. Okay. Now 3, which is the topmost requirement, that is what we have covered in A.2. Okay. So during the qualification also, you'll try to qualify. Okay. When you are able to follow A.2 requirement, if you have to control the hardness, okay, we'll learn about SS also. There are even control on the different elements also. That is not there in carbon and low alloy steel, controlling of elements, but it is there in SS. So we'll talk about that. So if you are able to meet A.2 requirement, okay, then you can use those materials which we have used, A.2. If you are not able to meet any of the requirements, you have to go in the lab, test that material in that condition which is required, and then qualify that material. Okay. So it becomes a very long process. On Y-axis, you have pH value, Vijay. Okay. the pH value of material is given on y-axis. Now, if I'll ask one question if you have understood or not. So partial pressure of pH or partial pressure of H2S, if it is 10 kPa, okay, you have to tell me which reason it will lie. If partial pressure is 10 kPa and pH value is 3.5, give me the reason number. If your partial pressure of H2S is 10 kPa and pH value is 3.5, what is the reason you'll be? Third. Absolutely right. Okay. So SSC reason 3. And for this, A.2 requirement becomes applicable. If you're able to qualify the material based on whatever requirements we have just seen, that is acceptable. If not, then there is a way to qualify that. Okay. So you can refer, annexure B for the qualification purpose. Okay. So that is also permitted. On Y scale, there's a pH value. Okay. Now, so that is all for carbon steel and low alloy steel. Okay. So these are the requirements for carbon and low alloy steel. The last one and the most important one, part 3, which is for SS. Okay. There are many other alloys also, but mainly we're talking about SS material, okay, stainless steel material. Okay. So austenitic stainless steel. Okay. If you are following, annexure A.2 is what we have to refer. Okay. And if you are following ferritic, then you'll be referring A.5. Okay. Yeah. So there is a table which is given for piping material. So you can see all the materials which we use are listed, which is A53. You have 106, you have 333 grade. So all that are acceptable for use in the carbon and low elastic. So ferritic stainless steel A.5, Martensitic A.6. We are talking about the annexure. Okay. Then you have Duplex, which covered in A.7. Okay. So now we'll see SS. There are very detailed requirement. So we'll see one by one. Okay. So are you ready to see the requirement for SS? For carbon steel, it was very simple, mainly linked with hardness control. Okay. And only one parameter, which is partial pressure of H2S. Right. Here you will see other parameters. You'll see chloride concentration. For Duplex, you will see Pren number. Okay. Now this is the first requirement. Austenitic stainless steels. There are limit on the multiple content of different elements. Like carbon should be limited to 0.08 max. So that is where you'll see 304, 316, 321, everywhere that carbon content you'll be able to qualify if it is, because 304 also, that is the max limit. Okay, so you'll be able to qualify that content easily. Chromium, minimum it has to be 16%. Nickel, 8% minimum. Phosphorus, 0.05, 0.045 max. Sulfur, again, limit on max, because these are kind of impurities. Okay. So those are limited in the max side, 2% and silicon. So mostly it's in line with the standard grade you procure from the ASME material. Okay. So don't think it's a mismatch with, in any composition. It's completely aligned. So if you purchase 240 plate by using the specification of ASME, you will be able to fulfill that category. So you don't have to identify or limit them separately. Now, this is very important. Okay. Now, this talks about the uses of austenitic stainless steel, which covers your 300 grades apart from 316L. 316L, there is a different requirement. So we'll see next to it. But all the austenitic stainless steel, which are 300 series, the requirement starts with, how to read this table. If my chloride content, I'll start with chloride. If my chloride content is maximum 50, chloride content is not more than 50 milligram, okay, then there is no limit on which temperature you can use austenitic still. There is no limit on the partial pressure of H2S. There is no limit on the pH values. You can use anything which is there if chloride content is limited to 50 milligram. Next, if your chloride content, if you have anything, pH also anything, the temperature, if you are having 60 degrees Celsius and the partial pressure of H2S, you can go up to 100 kPa. Okay. In that case, okay, if you're using that SS only till 60 degrees Celsius, okay, for the partial pressure of 100 of H2S, there is no limit on the chloride content and no limit on the pH values. Does it make sense, guys? Does this table make sense? How to see the requirement? If I have to use a 304 plate, okay, if my temperature is 100, temperature is 100 degrees Celsius. Okay, just listen to the question. So even if you you have not understood till now, don't worry. With that question, you'll be able to understand. Okay, if my temperature is 100 degrees Celsius, okay, can I use for that temperature? I'm not saying anything else. Can I use that material? Okay, SS material for that service if my service temperature is 100? Yes or no? No other requirement. Only I'm saying is the temperature is 100 degrees Celsius. Nothing else is known. So your answer will be yes or no. Can I use SS for 100 degrees Celsius? The answer will be yes. Okay. Now, when it will be limited, when you will say that, no, I cannot use, what should be the other condition? In which case, I will not be able to use stainless steel beyond 60. Partial pressure, if it is exceeding 100 kPa, H2S partial pressure, nothing related to chloride for this. Okay. So if my partial pressure of H2S is exceeding 100 kPa, in that case, I cannot use beyond 60. I can use up to 60 for partial pressure till 100 kPa. Okay. Now, in that sense, if I'm meeting the first two requirement, there is no limit on the chloride content or pH value. Okay. Does it make sense? Guys, I can have any chloride content. Okay. So it's very simple. Okay. There are two requirements which are mentioned for austenitic stainless steel. Okay. Now this table is apart from 316L. For 316L, we'll see the different table, which will come next. Okay. What we are talking about is austenitic stainless steel apart from 316L grade. Okay. What code says? Okay. First, think about the chloride content. Okay. My chloride content can be lower than 50 or more than 50. Yes or no? Forget about everything. Forget about temperature. Forget about partial pressure. Chloride content can be more than 50, can be less than 50. Yes or no? Chloride content can be more than 50, can be less than 50. I need few more yes. Okay. I'm telling you to forget everything else. I'm only talking about the chloride content. Chloride content can be more than 50, can be less than 50. Yes. If the chloride content is less than 50, is there any limitation on austenitic stainless steel? If the chloride content is less than 50, is there any limitation on the stainless steel? There is no limitation. Okay. Yeah, as per table, no. So, table is what we have to follow, Alfredo, right? Because this is the NACE requirement. Okay. Now come to the next thing. If my chloride content is more than 50, okay, I'm having 100 milligram chloride content. What I'll have to see next? What is my partial pressure of H2S? Okay. Partial pressure of H2S. If partial pressure of H2S is less than 100 kPa, can I use SS? Chloride content is 100 milligram. Partial pressure of H2S is less than 100 kPa. Can I use austenitic stainless steel? The answer is yes, but temperature has to be checked. I can use it, but not more than 60 degrees Celsius. Is that clear now? Is that clear? Make sense now? Great. Okay, very simple. Nothing to be confused about. See, apart from that, okay, these requirement, your material has to be solution annealed. Okay, there are other heat treatments also which are mentioned, but we are more familiar with solution annealing of SS, so I'll talk about that. So it has to be solution annealed, and it has to be free from any cold work. Cold working is not permitted, and that cold working which is used for the enhancing the mechanical properties. Many times by doing cold working, we enhance the properties, we increase the yield strength. Okay, so that kind of SS is not permitted. Make sense to everyone? So these are the two requirements for austenitic. Now come to 31603, that means 316L. This requirement is for 316L. Okay, this is temperature. This is partial pressure of H2S. This is chloride content, and this is the pH value. Okay. Now, let us try to understand this requirement. Okay, one by one. If my pH value is greater than 4.5, okay, chloride content, I can have up to 50,000. Partial pressure of H2S can be up to 1,000. Okay, so very high. And temperature up to 60 degrees Celsius. So 1000 kPa, 60 degrees Celsius. Make sense? Okay. Now, if my pH value reduces, okay, from 4.5, it's going to 3.5. You can see chloride content is drastically reduced. Now the chloride content cannot be more than 1000. Okay. Because chloride content further increases your acidity. Okay, acidic environment, and you're already going in acidic. Okay. So it's further limited, only 1000. Partial pressure of H2S still 1000. Temperature, you can use it up to 90 degrees Celsius. So good enough. Now, if we maintain the pH value same, 4.5, and if I want to increase the temperature, I want to use at 90 degrees Celsius. Okay, same pH value, I want to use the material at 90 degrees Celsius. In that case, it will be only able to take 1 kPa partial pressure of H2S. The chloride content is still 50,000, but partial pressure of H2S, by increasing the temperature, you can see it has gone down to 1. Okay. If I increase the pH value, if I'm going towards basic, if I'm going to 5, again, your chloride content is reduced to 5,000 kPa. You can go up to 10.2 and temperature 93 degrees Celsius. Okay. See, you don't have to remember any of these values. Okay. Now, these values has to be referred only when you have some requirement. Okay. You have the percentage of H2S, you have the chloride content, you have the pH value, and you have the design temperature. Then it will be very easy for you to refer this table. Yes or no? Do you think so? That if you have the value of H2S, see, like this referring maybe, looks like confusing, but if you have the requirement, like this will be the input for you. We don't have to control pH value or chloride content or partial pressure. All that will be given, even the design temperature. We'll have to just see whether 316L can be used for that application or not. Okay. So that can be decided by using this table. Okay. Very simple. Make sense till this point? Yeah. For SS316L also, it should be solution annealed and free from cold work, which is there because of the shaping or forming operations. Okay, so same requirement as it is for the normal stainless steel. Now going to ferritic stainless steel. Okay, so ferritic stainless steel, the control is by partial pressure of H2S and the pH value. Okay, so pH value is more than 3.5. I can use ferritic stainless steel for any temperature if my partial pressure is limited to 10 kPa. If partial pressure is greater than 10 kPa, I cannot use. Very simple. For pH value greater than 3.5, ferritic stainless steel can be used at any temperature if your partial pressure is less than 10 kPa. So basically 10 kPa you can consider as a limit for the ferritic stainless steels. Okay. Again, the controlling of hardness is required, 22 HRC. For Martensitic also, it's very same. Okay. Both ferritic and Martensitic in terms of chemical composition is very close to each other. So pH value 3.5, partial pressure of H2S 10 kPa. You can use it for any temperature or any concentration of fluoride. Fluoride is not a problem if your partial pressure is limited to 10 kPa. Okay. So very simple table. All the UNS numbers are also mentioned. Now talk about duplex. Okay. What is duplex? If you have to explain in a very simple terms, what is duplex stainless steel? Ferritic and Martensitic or austenitic with ferritic. So sometimes we'll get confused with ferritic and Martensitic. It is mix of ferritic and austenitic. Make sense? Okay, someone also asked what is NDS. Okay, so basically sulfur resistant, still it is not evolved. So it says, if you read the notes, so no data submitted for sulfur content. So if an NACE committee is not aware of that result, so maybe in future you will see some values for that also. Okay, so till now it's not available. So data not submitted is what has been shared. So yes, it's a dual phase duplex mix of ferritic and austenitic. Okay, so it has property of ferritic in terms of low temperature because it does not have so good impact properties. It can go up to -80 degrees Celsius. but below that it starts creating problem. While ferritic behaves very similar to carbon steel, okay, in terms of low temperature. So if you see for duplex, there is a Pren number which comes into play. Okay, now what is Pren number? What is the full form? What do you think Pren is? If you have used or seen any time, what Pren stands for? Pitting resistance equivalent number. Yeah. So that is given based on the percentage of certain elements. What are those? Chromium, molybdenum, tungsten, and nitrogen. So based on percentage of these elements, the Pren number is decided, okay, for the duplex stainless steel. So it's a very, very big parameter for duplex. Okay. Now, you may also heard of super duplex. What is super duplex? 25 CR. If your F-Pren is more than 40, if your F-Pren is more than 40, we call it as super duplex. Okay. So here, if you see for duplex, in terms of chloride content, you can see 180,000 milligram. Partial pressure of H2S again is limited to 10 and 20 for super duplex. Okay, 10 for normal duplex. So 10 kPa, very similar to what you have for ferritic, okay, and martensitic. But here the maximum temperature is limited to 232. Okay, and the chloride content definitely you can have much higher. Okay, so if you see these, if you have chloride content less than 50 mg, then there is no other limitation. You can use for any temperature, any partial pressure, okay, which material obviously can withstand.
For in-depth training, and to learn more about these courses, register with the link in the description.